actually, that the psychiatrist didn't need to give over her notes to the court in the litigation against the person who shot the police officer. So here, the privilege between the psychiatrist and their patient was maintained. However, there's a limit to that value. So when we go to the practical validity column of the client interest row, in Tarasoffy Regions of California, the court held, in contrary to the holding in Jaffe, that there's a limit to this privilege between the psychiatrist and their patient. In Tarasoff, the patient had told their psychiatrist that they intended to kill this woman, and then went on to kill this woman. And the court held here that because the psychiatrist knew that the patient was a potential danger to this woman and had expressed the intention to harm her, that practically, the concepts, the purpose of the psychiatrist-patient privilege does not apply here, because it's more important to keep this woman alive and prevent her attacker, more than it is for the attacker to feel comfortable, divulging that information to his psychiatrist, which is the principle that underlies Jaffe. And yeah, the rest of this table I'd be happy to flesh out in the poster session or in the paper. Each box is described. Thank you.
Thank you, Amika. Our next paper is Utility Functions for Human-Robot Interaction.
Yes, let me just share my screen. Okay, can you just confirm you can see my screen?
Yes.
Okay, can I begin? Okay, so hello everyone. So my name is Bruno Yoon, and I'm a lecturer at the University of Aberdeen, and today I'm presenting one work we did with Madalina Croitoru from the University of Montpellier and near Oren from the University of Aberdeen. So the work is called Utility Functions for Human-Robot Interactions. And we have a context where we have words, and actually our words are mostly symbolic. So they are sets of propositions, and agents, they can navigate through those words using a transition system and actions. So we have that each edge in this transition system is an action. And we also have utilities that tell us how good a word is. So for example, if you have an agent which is here and he push a child into a lake, then you go into a word with a negative utility. And the problem with that is that if you tell your agents to just optimize the utility he gets from this transition function, then he may, for example, push a child in a child and then rescue him and then push him again in order to optimize this utility function. So then you may ask, why not just go into this transition function, and maybe if we tweak the utilities, then maybe this behavior won't happen. So I guess you could do that, but the approach we had was to, instead of just modifying the utilities of words, what we are doing is we consider sequence of words. For example, here W1, W1, W3 means that we were here and then we move here by pushing the child into a lake. Here going home. This one is, okay, we were here, we pushed the child into a lake. This one is, we were here, we pushed the child into a lake, we rescued him, and then we went home. So then once we have those sequence of words, the idea is then how to correctly give numbers to those words, saying whether this sequence is better than this one, whether this one is better than this one, and then identify good sequence of words. So this is a context. So to do that, to associate numbers to do sequence of words, we propose some kind of aggregation function. So this one is usually the one that is used in the literature. So this one, for example, mean, we just take all the words in a sequence and then make the mean of the utilities. The blame one would be to only look at the word where we have negative utilities and then do some kind of mean. In this one, it's a bit maybe more clever. It looks like the blame one. We look at the negative word, but we also take into account the occurrence, right? So the more you encounter negative or word, then they count less. Okay, so that the repetition aspect decrease over time. So we gave some kind of aggregation function, but we also wanted to study desirable properties. So for example, this one, non-recovery, means that, for example, if this one is preferred to this one, then even if we do good actions or we go through words with positive after that, it will never be as good as this one. So you cannot redeem yourself by doing better actions afterward. Loss conservation means that if you add words and the outcome is worse, then this added thing, that the added sequence that you added will have a negative utility. Redundancy means that if you go through words again and again, it should have a lesser impact on the utility. Independence means that if you have aggregation function, they should only take into account the word that are actually in the sequence. The decreasing and increasing, decreasing benefits, increasing losses means that even if you gain benefits, they should decrease over time. Increasing losses means if you have loss, they should also increase over time. And then you have some kind of properties about initialization. For example, if you have only this word, should the aggregation associate a value of 0 or the utility of the word? So if you didn't do any actions, and then you have properties like additivity, which looks at, well, if you add a word that has a positive utility, then your aggregation function should increase the value or decrease the value if you have negative utilities. So that was a very, very quick overview of our theoretical work. And so there are many things you can do. You can have more aggregation functions, add desirable properties, and you can also explore other parameters, because here we only have occurrence, but you can also explore the order of the words or take that into account into aggregation functions. Thank you very much. You have the QR code if you want to have a look at the paper. And thank you for giving me time to explain this one.
Thank you, Bruno. Our next talk is by Kantwon on Playing Dumb to Get Smart, investigating the influence of a learner's age on the permissibility of robot deception in an educational scenario.
Can everyone see my screen?
Yes.
Yes, awesome. Well, hello, everyone. I hope everyone's doing well. I'm excited to be here to talk about my work. Or actually, maybe I'm not excited to be here. And maybe I actually don't care if you're doing well. You really have no clue. You don't know me. I could just be lying, because humans literally lie about everything all the time. And as we talked about before, this notion of lying is kind of a rebellion or disobedience against these social norms that a lot of cultures kind of teach. And this in itself is interesting, but it's also interesting as we start to think about how we're designing robotic systems and AI systems to mimic and learn from human behavior. So for instance, in 2017, researchers from Facebook and Georgia Tech were creating a chatbot that learned to negotiate based off of like human data. And what they found was that there was this completely emergent behavior of lying. The system just learned to lie because that's what humans do. And so therefore, this begs so many questions, but one in particular for the work that I'm having now is the question of, who is it acceptable for a robot to lie to? Who is it acceptable to kind of break these social norms to lie to? And so in addition to being a PhD student, I also am an instructor for a really large, like 1,000-person introductory computer science class. And I will say, I take great pride in lying to my students. I lie all the time for their benefit. I lie to simplify things to help them learn. And my favorite type of lying is when I'm working one-on-one with a student and they're explaining things and I just play dumb. Like I have no clue what they're talking about, just to get them to explain stuff more. And so this whole notion of learning by teaching, of course, is not new. And even in the robotic system, or in the robotic realm, it's also not new. There's systems that people have created to have children and learners learn by teaching a robot. But then I had this question of, So how do we view this idea of playing dumb or lying to someone to get them to learn better? How do you view that differently if there's a human doing it as opposed to a robot? And then also, how do we view this permissibility based off of the age of the person who's being lied to, whether they're a child, an adult, or an elder? And so we had an empirical study where we had a mixed methods approach where we had 90 Mechanical Turk workers and 6 in-person participants, where for the Mechanical Turk workers, we ran them through a between subject experiment with 6 different cases where it was either a human lying or a robot lying. Either a child was being lied to, an adult was being lied to, an elder was being lied to. And these were all text-based kind of scenarios that people were reading. And for this 6 in-person people, we had them look at all 6 of the scenarios. And so then we asked them questions about permissibility in the context of appropriateness. Does this action make sense? And how natural is this? And also to add qualitative information, we then had semi-structured interviews for the in-person people. And so some interesting things that we found was that when we asked the question about, like, is it appropriate what was done in this scenario? If we look at just the notions of a child being lied to, people find it perfectly fine for humans to lie to children. That, of course, says something about humans. But interestingly enough, people did not find it very acceptable for a child to be lied to. So when we're thinking about these notions of disobeying and like lying against social norms, maybe people aren't feeling as it's best for children to be the recipients of that rebellion or disobedience. And this wasn't necessarily the case for the robots the elders and the adults. But then we also asked the question of, does this make sense? Does it make sense what the robot or human was doing in the situation? Interestingly, we saw that for every case, people said that it made sense that the robot was lying in order to help a person learn, more so than a human lying in that situation. And so this also kind of adds even more information about this notion of, like, is it acceptable or not? Because people can say it's inappropriate, but they also agree that it makes sense. So this adds more nuance into us asking the questions of, should robots be lying or should robots be disobeying these social norms? And so also in this study, we have a bunch of qualitative data, thematic analysis, interviews, quotes, and all that stuff, which I'm more than happy to talk about with people in the poster sessions. And so that's basically it. So thank you. And I look forward to our questions and discussions in our poster sessions. Or maybe I don't. Maybe I'm not looking forward to it at all.
Thank you, Kantwon. I am looking for it. And next is Arnold talking on his paper on only those who can obey can disobey, the intentional implications of artificial agent disobedience.
Hi, everyone. Thank you. I'm Thomas Arnold at Tufts University's HRI lab, presenting a work with Gordon Briggs, who I think is here with us as well, and Matthias Scheutz at HRI lab. And we have a paper, only those who obey can disobey. And our paper is motivated by a phenomenon that I think we've all encountered about how robots are represented in public, how they the implications of how they're represented for how we understand how they work. And this is one comical tongue-in-cheek instance, the runaway robot. This is just a Roomba that crossed a certain threshold after a certain update. But we can see how easily people attribute these notions of rebellion, making a break for freedom. We've heard the robot overlords taking over the world is in the caption. And so we really want to push back a little bit on the notion of disobedience itself in our paper. And so we discuss in the paper, how do we describe disobedience relative to other behavioral descriptions of non-conforming behavior, divergent behavior, errant behavior, unpredictable behavior, any behavior that is not expected or desired or in line with certain goals. That doesn't necessarily mean it's disobedient. What we explore in the paper are the implicit intentionality ascriptions that are wrapped up in disobedience. See, implicit norms, and we've already talked about norms. Dylan's talked on norms already. Some of us here have already talked about norms. What is wrapped up in that, and what would desirable disobedience look like in context. So we discuss what kind of criteria are woven into disobedience, understanding an instruction, knowing what an obeying looks like, something that has no training at all. I could yell to an animal across the street to get me, a coffee, but its refusal to do that has nothing to do with disobeying. There's no traction of obedience there. And we dip a little bit into child psychology for human-robot interaction around how intentionality is connected to what is identified as a disobedient action, as opposed to an accidental action or something that is, unintentionally divergent. And we recognize, and it's great to have Dylan's talk that included some work on inverse reinforcement learning. We can see that there's some interesting ways in which reinforcement learning can talk about obedience and disobedience in terms of rejecting an instructor's suggested action, but it's worth keeping track of what's not there in terms of external symbolic representations of a rule or a norm, just the instructor's designation of an action, and then you judge by utility or the rationality of the instructor. But explicit representations that could be shared across agents in a multi-agent environment, references to norms, are not necessarily there. And so, we suggest that divergent behavior, exploring an environment divergently may not license the term disobedience necessarily. So we talk about local versus global as a way to frame disobedience. And we use a simple example of a hospital robot rejecting its normal request to take something somewhere because of a safety protocol. There's a more global principle that justifies the local disobedience. And this allows for certain logical operations, modal operations of what's permitted, what's obligated, as well as differentiating different layers of directives, local and global. And for us, this really is about interactive demands for human-robot interaction. Because of how easily ascriptions of agency and intentionality can be manipulated, can be elicited, it's really important for us not to police the term disobedience and say it has to meet the high standard of a full ethical agent necessarily, but that we're a little bit more careful in terms of when it is ascribed. An errant agent, a divergent agent, is not necessarily disobedient in the fuller sense of having a capacity to obey an instruction and being able to justify explicitly why disobedience is called for. So this is our way to, again, to collaboratively kind of think through a little bit more clearly in a little bit more fine-grained manner when we attribute that concept. Thank you so much.
Thank you, Thomas. Next is Walterio talking on rebellion and disobedience's useful tools on human-robot interactions research, a handheld robotics case. Walterio, we can't hear you. I can't hear you.
Confirming I can't hear him either.
Are you able to hear me? Hello?
Yeah,
Yes, now.
now we can hear you.
Okay, I don't know what happened. I tested it just a moment ago because, maybe a rebel computer playing games with me. Okay, so today I'm going to talk about some research that with my team at the University of Bristol we've been doing in terms of rebellion and disobedience in the context of this new type of robot, which we call handheld robots. So handheld tools have existed for a couple of million years in hominids. And despite all the progress in terms of the advance in terms of handheld tools, they have remained pretty much essentially just following everything that we do and obedient to our intents and purposes. And this is precisely what interests us from the point of view of creating robots that are different from what you might find out there, because external robots is perhaps the most typical type of robot that we imagine, a robot that is meant to be working on its own and perhaps cooperating, but still totally external to the person. And then on the other side, you can have robots that are very close to the person, perhaps wearable robots, that are more intimately linked to the way in which we move and the places where we want to go. Handheld robotics, we see that as something that is in between these two extrema. And the idea is that handheld robots behave as conventional handheld tools, but they have actuation and they have task information. So they know what the task is and they can potentially help us. We see handheld robots being able to be used in a range of applications, pretty much everywhere where handheld tools are used. And they tap into something which in robotics is called the Moravec paradox, which essentially says that humans are very good at doing things that robots struggle and the other way around. Robots can be very good at certain things that humans will struggle. So back in 2013, we started to work on this type of handheld robots. And we created one of the first prototypes that had disobedience as part of helping. So what you can see in this video is that there is the handheld robot and it's helping the human to perform an activity which is placing tiles, picking up and placing tiles in the correct pattern. And as the task progresses, there is a moment when all the black tiles have been placed, and if the human tries to pick a new black tile, the robot actually refuses to do that and actually gestures and points towards the tile that you need to pick. So in this case, is the most classic type of disobedience that you can engage in robotics, the one that is trying to benefit the user. But we have also investigated rebellion. In this case, the robot actively tries to do the opposite of what the person wants to do, and we find that this is useful. This task is a different robot, but it's also a handheld robot, and the robot is helping the user to place these virtual tiles in this screen, and the robot has a gaze tracker. So with this gaze tracking, we can actually predict with very high accuracy what is what the person wants to do, and we can actually rebel against what the person wants to do. And we actually do this on purpose. We do this on purpose because in this type of human-robot interaction research, it's very easy to get very poor signals when you want to predict intention. So we predict where the person wants to place a tile, and we actually go against what the person wants to do. And this helps us to improve the signal of knowing that we're actually doing the right thing. So we have three modes. The robot follows what the person wants to do. So we use our predictive model. We randomly choose a location, or we rebel against. So we know what the person wants to do, but we do something that is valid, but very opposite to what they want to do. And with this, we can show that the level of frustration increases as expected, but it also gives us better signal to understand that we're able to predict what the predictive system is intending. We do think that there are other cases where rebellion and disobedience can be useful in human-robot interaction, and I will be happy to take any comments or questions afterwards. Thank you.
Thank you, Walterio. We now have two talks on of papers who got accepted to the first one to AAAI, the second to AMAS. The first one is will be presented by Yotam. I don't think so. Disagreement-based policy summaries for comparing agents.
Hey, can everybody hear me all right? Great. So, hi everybody. Thanks for having me. Okay, so I'm going to show you, talk today about a method that we developed for summarizing disagreements between agent comparisons for the task of explanations. So, agent comparison. The market for autonomous agent solutions is growing. I probably don't need to tell you this. In transportation, agriculture, everything. And so more agents are coming, right? And we need methods to compare between them. And these methods that are available today are usually numerically based, right? So when we come to compare methods or agents, we usually do it by some kind of score or reward function or the number of parameters or their complexity, some numerically based value. And this is good if you understand the literature, but it's not so good if you're a layperson that doesn't understand and just wants to purchase or use an autonomous agent that a company is supplying, let's say an autonomous vehicle, right? So what is missing? What's missing is some user-centered approach for comparing these agents to one another. And most importantly, there isn't any method today that is able to convey or compare agent behavior. So this is very important, and that's where we come in. So what we did is we built upon an existing approach for explanations called agent policy summarization. And the key idea in this approach is that given past interactions of the agent with the environment, this is, I should say, in the MDP and reinforcement learning formulation, so past interactions of the agent with the environment, we can identify the most important states by some importance criteria, and then generate a summary video of the agent interacting in these states and portray this to the users, so that it can understand through the video the capabilities of that agent. So the most common method that utilizes this approach is the highlights algorithm. And the importance criteria there is the difference between Q values in these states. So can we use this method in order to compare our agents? Well, we can, but there's a big limitation here. And that's the fact that the videos generated by this approach are independent for every agent, right? So if we want to compare two agents, the videos for each one isn't dependent on the other. Therefore, what can happen is we can see the both agents in the same states, because these are the important states, making the same actions, and we don't get any information about the differences between them. Or on the other hand, we can see these agents in totally different situations, and then the comparison won't be fair. How can we know what this agent would have done given if it was in that state? So this led us to devise a disagreement-based approach for these summaries, where the idea is to show the disagreements between the agents given the exact same state. And we define the disagreement as such, a conflict in actions, given that both agents have seen the exact same state or observation. And the advantages of this method is that the comparison is fair because they see the same state. It's dependent and contrastive because we can see what each one would have done. And it's also visually appealing for the users who can actually see in the environment the agents go in separate directions. So the gist of our algorithm, called the disagreement algorithm, is that we force two agents to act in parallel until reaching some disagreement state. In that disagreement state, we allow them to split off, each going their own way, and we record this trajectory that each one arrives at, and we also rank it. So this way, we after these number of steps that they split, we return them to that disagreement state, and we force them to keep progressing together until reaching the next disagreement state. And we rank these disagreements and allow and generate a video, as the one you're seeing here, that shows the most important disagreements. So to evaluate our algorithm, we chose two tasks. The first was a superiority task, showing letting participants choose which agent they think is superior. And we did this in the Frogger domain. And another one was behavior identification, seeing if participants were able to correctly identify behavior traits of agents. And for that, we used the highway domain, which doesn't have a specific goal to it and is more, it's easier to portray agents with different traits and different behaviors. And the conditions were the highlights algorithms, two separate highlights for each agent versus the disagreements combined of both agents. And in short, the results that we found were that in the superiority task, the disagreements algorithm significantly improved the user's ability to identify these superior agents. And in the behavior identification task, the disagreement summaries were equivalently as useful as the highlights, which was proven to be better than random in previous literature. Thank you very much.
Thank you, Yotam. And our last talk of the session will be presented by Peiju, evaluating the role of interactivity on improving transparency in autonomous agents. This paper was accepted to AMOS.
Can you see my screen and can you hear me?
Yeah.
Okay. Hello, everyone. Thank you so much for coming to this presentation. My name is Peiju Qian, and I'm a PhD student in computer science at Rice University. I work with Dr. Vipul van Helker on problems related to human-robot interaction, explainable AI, and human-centered AI. Have you ever wondered how it is like to be a firefighter? Interestingly, firefighters have a work schedule much different from many other industries. In most cities in the United States, firefighters work 24-hour shifts, and they work 10 of the 24-hour shifts per month. This means that firefighters might need to work in highly stressful situations while being tired and sleep deprived. In late 2020, the city of Los Angeles became the first city in the United States to add a firefighting robot to their ranks. The Los Angeles Fire Department chief described the robot as a game changer for his team. Handling emergencies require firefighters to react quickly and be prepared to any fast-changing situations. During such situations, firefighters want to make sure they don't waste time figuring out how this robot works, but they want to use the time to fight fire. So in order to work effectively with robots, robot users, who are the firefighters in this example, need an accurate mental model of the robots they work with. Having the correct mental model of the robot will ensure safety, avoid unintended side effects, and build users' trust in the robotics system. To use the robot correctly, the user should have the correct mental model. Otherwise, the robot might introduce delays in fighting fires. We define user model as a probability over different user policies. So prior to training the users, this user might not have the correct model. In this example, the firefighter holds two hypotheses about the robot's policy. In the first scenario, the robot clears the debris, then puts off the fire. And in the second scenario, the robot clears the debris. In the second scenario, the robot goes around the debris and directly goes to the fire. So which one of these hypotheses is the correct robot policy here? In our framework, we present different user hypotheses using a belief over possible robot models. Then we update the user's belief using Bayesian theory of mind. Our research looks at training users of robots so that they have accurate mental models. Our goal is to train users prior to task deployment so that they have the correct belief over robots' behavior, and so that they can accurately evaluate what the robot will do in a novel situation. In this example, before training, the firefighter holds a uniform belief over the hypotheses. And after training, we want the firefighter to have the probability of 1 over the correct robot policy. To categorize the research in this emerging area, we view it from the lens of pedagogy. One categorization of human-to-human teaching strategies is based on the use of direct versus indirect instructions. For example, lectures are a form of direct instructions. These instructions are prepared before a class, and they often aim for a large audience without much personalization or independent learning. And prior work in explainable AI has mostly focused on generating direct instructions from a robot policy. On the other hand, sometimes we look up tutorials or practice problems on our own, and these are a form of indirect instructions. These instructions target the specific questions we have as an individual student, and they involve a high level of personalization and independent learning. So both these two types of instructions are effective pedagogical methods, but both approaches are missing key features. On one hand, direct instructions are missing the independent learning and personalization features, while indirect instructions are missing the guidance from an expert. Recognizing these limitations, our framework adopts a hybrid teaching strategy where the AI teacher first generates instructions before interacting with the user. These instructions are generated based on a cognitive human model. During the time where we are training the user, users can create their own scenarios in an environment and self-explore what the robot's action would be in a specific scenario they created. To evaluate our approach, we conducted a user study with 24 participants from Rice University. We designed 3 robotics tasks, all inspired by real-world applications. The first task is the search and rescue robot. The second is a navigation robot, and the third is a recycling robot. For each task, we allowed 25 instructions to learn for the participants to learn about the robot. From the user study, we see that the hybrid strategy, which is our approach, results in higher scores than using direct instructions only in both predicting robots' actions. And we also see from the subjective perspective, participants have a better learning experience with hybrid than direct. Our framework has broad up implications for ensuring mutual trust and transparency during human AI teamwork. As an immediate application, our approach helps human users make informed decisions regarding if and when to use AI agents. When users have accurate mental models of the agents they work with, they can better predict an agent's rebellious behavior and understand why the agents would have such behavior. This is important in human-agent interaction because unexpected behavior from both agents and humans might result in catastrophic consequences. And similarly, such understanding should go both ways. It is important for the agent to have an understanding of the humans they work with. Our work can help agents estimate the human user's theory of mind, for example, the human user's mental model of the agent, so that the agent can decide when it should rebel or disobey. So that wraps up my presentation. Thank you so much for having me.